Log on, tune in, find out. Another good idea from Cambridge.
I realized that I will say a few things that go straight against what Jordan has said this morning in the first talk. Here's an outline of my talk. I will start with an example from marketing, and then I will give a few examples from health, and then I will describe the Bayesian optimal design framework that we use to construct designs for discrete choice experiments. I will show you the model we've used for this work, the information matrix that we derived from the model. And then I will discuss the various approaches that have been used in the literature, the locally de-optimal design approach, the utility neutral design approach, and then the approach that we use in our work, the Bayesian de-optimal design approach. Then I will tackle the problem that motivated the work we did I will tackle the problem where we have many attributes in our choice experiments, and for this problem we developed a two-stage design algorithm. I will discuss that in some detail, and then I will come up with several illustrations, and I will compare all the different designs that we derived. Here's the first example that I have. What you see here is a choice set in a choice experiment to figure out what the preferences of users of a specific statistical software program are. The statistical program software program is the JMP or JUMP software. So, and the goal of this experiment was to figure out how the users liked to have their results presented. And so here you can see two different alternatives, and on this screen here it's very hard to see the differences between the two outputs, but the output on the left has a bluish background, hard to see I admit, and the one on the right has a white background. Also there's a difference in the background color of the graph. Here you can see quite nicely that this is a light gray background. Here we have a white background. And the idea was that in this choice set, the respondents would indicate the alternative they like best, the output display they liked best. The respondents got to see several choice sets. So here you see a next choice set. Again, the background color changed a bit. The way the graph was framed was different. So here we have no lines around the graph, but here we have some lines so that the complete graph is framed here. So these were subtle differences in the output display, and the idea was that the respondents chose between the two alternatives in every choice set. In this experiment, 7 attributes were varied, and here you can see the names of all these attributes in the columns: the report background color, the picture background color, the graph background color, and so on and so on. The last attribute was the way in which the y-axis title was presented on the output displays. 6 of the 7 attributes had 2 levels, the last 6 here, and the first attribute had 4 different levels. And here you can see the first choice set again, now with the levels of all the attributes, of the 7 attributes in the 2 output displays in this choice set. And what was special about this choice set is that the 2 output displays, the 2 alternatives, only differed with respect to 3 of the 7 attributes. Only the report background color was different for the 2 alternatives, the graph background color, and the frame line color. The levels of the 4 other attributes were held constant. Similarly, in the second choice set that you saw, only 3 of the 7 attributes had different levels. This time the picture background color, the frame that was used, and the outer graph rectangle that was used or not used. And again, the 4 other attributes had levels that were held constant. So this was the kind of design that was used, and this kind of design is called a partial profile design, because you change only a little bit of each alternative, a couple of the alternatives, a couple of the attributes in every alternative. We call that a partial profile, as opposed to a full profile. And a key feature is that some of the attributes are held constant. So you will see the term constant attributes appearing pretty often in this talk. Now, why do people do this in choice experiments? Well, to keep the cognitive burden for the respondents limited. It's believed that it's hard for people to evaluate lots of levels of lots of alternatives in choice sets. And that's why we try to keep the cognitive burden limited. We only vary a couple of attributes in choice sets. What is this good for? Well, first of all, it prevents respondent fatigue. It avoids inconsistent choices by people who are not motivated to complete the survey anymore. It avoids lexicographic choice behavior, and it also limits the consequences of lexicographic choice behavior. So this is why we use this approach, partial profiles involving constant attributes. What is the lexicographic choice behavior? This is what I mean by this is the kind of choice behavior that we saw this morning in the first talk. There, each of the respondents basically focused on one attribute only and chose, for example, the lowest level of that attribute all the time. That's what you could call lexicographic choice behavior. And people do this maybe because that's for them the only attribute that's important, that's a possibility, but people also do this when things get too complex for them and they just want to complete the survey as quickly as possible. Now, this partial profile ID is not only relevant in marketing when you, for example, want to figure out what output display people like for their software programs, but this partial profile ID is also important for discrete choice experiments in health. What you see here is a screenshot of a paper by Julia Witt and co-authors from the University of Melbourne. In this paper, the researchers carry out a discrete choice experiment using a so-called blocked attribute design. And what they mean by that blocked attribute design is basically that they have 3 different choice experiments. In total, they wanted to study the impact of 11 attributes on people's preferences, on people's utilities, but 11 attributes was considered way too many. The 11 attributes were split into 3 sets of attributes, and for each set of attributes, a different discrete choice experiment was done, because it was believed that 11 attributes were way too many for respondents to handle. So that could have been an application of the partial profile approach as well. Here's another screenshot from another paper by Mark Sculfer et al. Here too, there were a lot of different attributes that were studied in the experiment, and therefore the researchers split their study in 2 parts. They did 2 choice experiments instead of 1, and in the first choice experiment they used 3 unique attributes and 2 common attributes, 2 attributes that were common for the 2 studies they did, and in the second study they considered 3 other unique attributes and again the 2 common attributes. This was again done to limit the cognitive burden of the respondent. And for those of you who don't believe that the cognitive burden of doing choice experiments in health can be quite big, here you can see a screenshot from a paper by Brazier et al. What you can see here are all kinds of dimensions on which our health can be evaluated, like physical functioning, role limitations, social functioning, pain, mental health, and vitality. And for each of these dimensions we have various levels. So as you can see, we have between 4 and 6 levels for each of these dimensions. Now, if you want to figure out how people value these different levels for each of these dimensions, you can do a choice experiment, and the choice experiment would have choice sets that look like this. So here we have 2 alternatives, 2 different health states between which people can choose, and each health state is described by a level of each of the 6 columns each of the 6 dimensions we had on this graph. Now, if you have to evaluate 20 different choice sets, each of those having descriptions like this, you can get quite tired and answers might not be fully reliable. So that's why we think the partial profile ID is a good ID. I think it's much better to be selective in the number of attributes you use in every choice set to try to keep the respondents with you when you do the survey. Now the question, of course, is how do we come up with a nice partial profile design? Well, for this we need to start from a model, and the model that we used in our work is the multinomial logit model, in which the probability that a certain alternative j in choice set S is chosen looks like this. That's a logit probability. And in this expression, the x vector describes the levels of the attributes in each alternative, and the beta vector is in marketing often called the pathworth vector, but that vector describes the preferences that people have for the different levels of the attributes in your study. And it's this beta vector that we want to estimate after collecting the data in the choice experiment. Now, once you have a model, for example, this multinomial logit model, you can derive the information matrix corresponding to that model, and the information matrix describes the informational content of your experiment about the parameters in your model. And the information matrix for the multinomial logit model has this structure. This information matrix is a sum of individual information matrices for every choice set. So this sum is over all the choice sets, starting from the first up to the last one, capital S. X sub S here contains the levels of the attributes that you use in choice set S. That matrix appears twice here. And then we have a capital P matrix and a small p vector. This capital P is a diagonal matrix that has all choice probabilities on its diagonal, choice probabilities of this form here. And this vector small p, that's a vector with again the same probabilities, containing the very same probabilities. Now, and what's the idea when you set up a design? Well, you want to optimize the properties of this matrix somehow. You want to optimize the informational content of your experiment, and you do this by seeking the design that maximizes some function of that information matrix. Now, unfortunately, in all nonlinear models, and so also in the multinomial logit model, the information matrix depends on the unknown parameters. So if we want to maximize that information matrix, we need to assume values for the parameter vector beta. And there are various ways in which you can do this. You can, for example, use the locally optimal design approach. You can, for example, use the local de-optimality criterion. And that criterion assumes that you use an educated guess, an educated point estimate for the betas, and you plug it into the information matrix. And then you maximize the determinant of the information matrix, or the logarithm of the determinant of the information matrix. That's the locally de-optimal design approach, which was introduced in the choice design literature by Huber and Sverina back in 1996. That approach is nice in the sense that it incorporates prior information in your construction of a good design for choice experiments. Negative point about this approach is that it completely ignores the uncertainty that you have about your prior information. Because you use a point estimate, just a single educated guess for your betas. One special case of a locally de-optimal design approach is the utility neutral approach that has been used quite a lot in the literature. In that approach, the educated guess you use is just a zero vector. You assume that all the betas are zero. In that case, the logit probabilities simplify substantially. The logit probability simplifies to 1 over j, 1 over the number of alternatives in a choice set. And then your information matrix looks much simpler, and you can prove a lot of different theorems, and you can show that some kinds of designs are optimal under this assumption that beta is equal to 0. That's the approach that has been used quite a lot in the literature. For example, Burgess and Street are probably the best known researchers in that area in choice experiments, but in Europe we have a strong group in that area as well, the Grossman, Grashoff, Holling and Schwabe group, who do very similar work and who derive designs that are often smaller than the Burgess and Street designs, but that are also optimal. Among the utility neutral designs, I would also classify the approach by Kuhfeld from the SAS Institute. Implicitly, the whole construction approach in the SAS macro for constructing designs, implicitly there is also the assumption that the betas are equal to 0. And if you use that approach, you typically end up with choice designs that exhibit minimum level overlap, and that's what's causing the problems that Jordan Louvière indicated this morning. That's when the separation problem occurs when you look at individual level data. That's when you have this lexicographic type of data. So that's another approach that you can take, the utility neutral design approach. And then I arrive at the third approach, the approach that we've been using, mainly the Bayesian d-optimal design approach. In that approach, we specify a prior distribution about the beta vector, and the idea is that that prior distribution describes our prior knowledge about the betas, and also the prior uncertainty that we have about the betas. And the goal then is to find the design that performs best on average over that prior distribution. Technically, the criterion that we use is this criterion. We try to maximize the integral of the logarithm of the information matrix evaluated over the prior distribution pi beta. And in our work we usually assume that the prior distribution is a normal distribution, a multivariate normal distribution, but there is nothing that prevents us from using log normal distributions or uniform distributions. It's basically the same machinery that you can use. It's the same logic that we can apply. Now, since we use the normal prior distributions, we can evaluate this integral very rapidly because we can rely on the quadrature scheme developed by Gottwald, Jones, and Steinberg in a technometrics paper in 2009. This quadrature scheme allows this integral to be approximated well at a relatively low computational cost. So that's the Bayesian d-optimal design approach, and the authors who introduced this approach in the choice design literature are Sander and Wedel, who were both working at the Dutch University at the time, but who have moved away now. So that's the Bayesian d-optimal design approach. So that's what we use to construct designs with partial profiles. Now, how do we do that? How do we end up with designs that have partial profiles? Well, first of all, we assume that the number of constant attributes and the number of non-constant attributes are given. We believe that this is a decision that should be made by the individual researcher who usually has done a lot of discrete choice studies of a similar type, so he knows usually what number of attributes respondents can handle, so what the maximum cognitive burden is that you should impose on them. So we assume the number of constant attributes and the number of non-constant attributes, which I name TC and TV here, that they are given. Then what we do is, our design approach is a two-stage design approach. In the first step, we determine the attributes that we hold constant. So we determine the TC constant attributes in every choice set. That's step number one. Then given that information, we determine the levels of the non-constant attributes. And for each of these two steps, the determination of the constant attributes and the determination of the levels of the non-constant attributes, we have two different approaches. And here you can see the two different approaches for the first stage, for the determination of the constant attributes. There we have an approach we call attribute balance, and the alternative approach we have is variance balance. And I will construct designs with both approaches. I will explain you in a minute what exactly these approaches are. And then in stage 2, where we have to decide on the levels of the non-constant attributes, we have a coordinate exchange algorithm that may or may not have a restriction. And I will also explain you in a minute what this restriction involves. So in total we have 2 by 2 is 4 different design approaches to try to find good designs with partial profiles. First of all, stage 1. What do we do in stage 1? What is attribute balance? Well, in that approach, the attribute balance approach, we try to make sure that every attribute is held constant equally often, and on top of that, we try to make sure that the number of times an attribute is held constant together with any other attribute is constant also. And people who are familiar with balanced incomplete block designs will immediately recognize these two requirements that we have here. Balanced incomplete block designs satisfy these two requirements. Unfortunately, balanced incomplete block designs do not exist for any possible experimental situation, and to cope with that problem, we developed an algorithm that tries to find a design that's as close as possible to a balanced incomplete block design in case none exists. I will not go into the technical details behind this, but you can do this relatively easily with an optimal design algorithm. You can find designs that are as close as possible to balanced incomplete block design. Now here is a balanced incomplete block design. This is a balanced incomplete block design involving 15 different blocks of size 2. And in these blocks you can find the integers from 1 to 6. And because of that, because we have 15 blocks here, 2 observations per block and 6 different levels in each of the blocks, we can use this balanced incomplete block design to construct a choice design with 15 choice sets, 6 different attributes, of which we hold 2 attributes constant. So the block size of your balanced incomplete block design determines how many attributes you hold constant in every choice set. So that's the balanced incomplete block design, and notice in the first block, in the first choice set, we have the numbers 1 and 2, and because of that, in our optimal choice design, the first 2 attributes are held constant. As you may see here, all the 4 other attributes have different levels in the 2 alternatives in the first choice set. In the second choice set, you can see attribute 1 and 3 are held constant. That's because in our balanced incomplete block design, we have the numbers 1 and 3 in the second choice set. So that's how we do it. How we use balanced incomplete block designs to decide on what attributes to hold constant. I will return to that example later on. Now that's the attribute balance approach. Every attribute is held constant equally often, and the number of times each pair of attributes is held constant together is also constant. That approach may seem nice intuitively, but it's not the best thing to do when your attributes have different numbers of levels. Here in this example, we have one attribute acting at 5 levels and some attributes acting at 2 levels. Because we have an attribute acting at 5 levels, we have an attribute for which we have to estimate 4 different betas if you use effects type coding, for example. So for this attribute, the 5-level attribute, we have to estimate many more things than for a two-level attribute for which we have to estimate only one parameter. And if you hold all the attributes constant equally often, then you do not spend enough effort on the 5-level attribute, for which you need to collect much more information than for the 2-level attribute. And that's what inspired us to have a look at another approach, the variance balance approach. We've named it the variance balance approach to determine what attributes to hold constant in every choice set. The idea is that we hold attributes with fewer levels constant more often than attributes with a larger number of levels. The reasoning behind that is that for attributes with fewer levels, we need to learn less. How did we do that technically? Well, technically we used a sort of weighted optimality criterion for the model that's behind balanced and complete block designs to figure out what attributes we have to hold constant in every choice set. Going into technical detail here would lead us way too far, but we have a pretty clever weighted optimality criterion approach, I'd say, and the weights that we use in that criterion are basically derived from some of the work of Heiko Grossman, from some of the theoretical optimal information matrices. That's where we got inspiration for the weights that we have to use. So that's it for stage 1, where we decide what attributes to hold constant in every choice set. Then there is stage 2, where we have to decide on the levels of the attributes which we do not hold constant. When we use the unrestricted coordinate exchange algorithm, and the coordinate exchange algorithm is a heuristic search algorithm to optimize experimental designs that's been around since 1995. What happens if you use that coordinate exchange algorithm is that sometimes attributes that you do not want to hold constant are held constant anyway. Apparently, it's statistically optimal to have level overlap for some of the attributes that you do not want to hold constant. And this is unelegant. You would ask your software for 2 constant attributes, and in some choice sets, you would have 3 constant attributes. That's unelegant, it might confuse the respondents, so we want to avoid that. That's what inspired us to consider also a restricted version of the coordinate exchange algorithm that avoids this level overlap at all costs. So in that approach, the restricted approach, only the attributes that, the constant attributes, they are the only ones that are constant. The attributes that you want to be non-constant, they should be non-constant. So that's stage 2, unrestricted versus restricted. So that's it. That's our approach, or 4 different approaches, I should say, to constructing partial profile design. And I will now describe some of our results using one specific scenario involving 15 choice sets of size 2, 6 attributes, 3 of which have 2 levels and 2 of which have 3 levels, and the final attribute has 5 levels. We assume a main effects model, and we assume that every attribute is effects type coded. So that means that for these 3 attributes here with 2 levels, we need to estimate 1 parameter. For these 2 attributes with 3 levels, we need to estimate 2 parameters, and for this attribute, we need to level. For this attribute, we need to estimate 4 parameters. We use the normal prior distribution, a multivariate normal prior distribution with this mean here. And so this mean vector has length 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Has length 11 because there are 11 parameters in our model because we use effects type coding. The first 3 numbers are the prior means for the 3 betas corresponding to the 2-level attributes. The next 4 numbers are the prior means for the betas corresponding to the 3-level attributes. And then the final 4 numbers are the prior means corresponding to the 4 betas for the 5-level attribute. Now, with each of these parameters, we also associate uncertainty, and we express this uncertainty using this variance-covariance matrix here, sigma naught. So that's the prior distribution we used, some prior distribution to get some good computational results. Now, the benchmark design that I will be using for this study is the full profile design, where we assume that the respondents can handle all 6 attributes at the same time. Their cognitive capabilities are unlimited and certainly much better than the undergraduate students I teach. Here's the design that we found. 15 choice sets, 2 alternatives per choice set, without imposing any restriction. And if you don't impose any restrictions, sometimes there are attributes that are held constant, because it turns out that this is statistically most efficient given the prior information that we've inputted, given the prior distribution that we've used. So that's the impact of the unrestricted coordinate exchange algorithm. Sometimes you get this level overlap, sometimes you get constant attributes. So that's the statistically most efficient design using the de-optimality criterion to measure the quality for our scenario here. And next to every design I will show you, we have put a vector, a 6-dimensional vector that indicates how often we hold each attribute constant. So here in this design, the first attribute is held constant twice. The second attribute is also held constant twice, the third one 3 times, and the last 3 attributes are held constant in none of the choice sets. That makes sense, because the last 3 attributes are the 3 attributes that have the largest number of levels. That's the 3 attributes for which we want to learn most. We have to estimate most parameters for these, so we don't want to hold them constant too often. And the de-optimality criterion figures this out, and you can see this because of these 3 zeros here. No level overlap for these parameters. Then let us have a look at the first couple of partial profile designs where we want to hold 1 attribute constant. Here we have the result of our algorithm that uses attribute balance and the unrestricted coordinate exchange algorithm. If we do that, if we use that algorithm, then in theory every attribute should be held constant equally often, but this is not true. For some of the attributes there is more level overlap than for others. You can see that the 2 level attributes are held constant more often than the others, even though we didn't really want that, even though we wanted to have attribute balance. That's a negative side effect of this unrestricted coordinate exchange algorithm. So from a practical point of view, that's a result that's undesirable. If we use the restricted coordinate exchange algorithm combined with attribute balance, then we get this nice pattern here where every attribute is held constant equally often as possible, given the number of choice sets and the number of attributes that we have. So that's a design that looks much nicer. 1 constant attribute in every choice set. Then for the variance balance approach, this is the design we get. Here you can see variance balance, and here the restricted and the unrestricted version of the coordinate exchange algorithm gave the exact same design. You can see that only the 2 level attributes, only the first 3 attributes are held constant, and each of those are held constant in 5 choice sets. So that's the pattern we get, 3 5s and 3 zeros if we use variance balance and the restricted as well as the unrestricted coordinate exchange algorithm. Then some designs involving 2 constant attributes. Here we have the result for the attribute balance approach involving the unrestricted as well as the restricted coordinate exchange algorithm, they resulted in the same design in this case. And you can see here that the attribute balance is perfectly fine. Every attribute is held constant equally often. Then for the variance balance approach, we got two different designs depending on the exact weights that we used. That's one design we got. In that approach, you can see again that the two-level attributes are held constant substantially more often than the other attributes. That's one design we got. And here's another variance balance design which looks very similar, which has similar numbers for the constant attributes. So in all these designs I've shown you are designs that we obtained using that Bayesian d-optimal design approach. We also did the same exercise using our algorithms, but this time assuming that beta is equal to 0. So taking the utility neutral approach, and using that utility neutral approach we also calculated optimal designs for the same scenario. Here, for example, we have the full profile design, and that full profile design is a perfectly, well, that's the kind of design you get when you use, for example, the SAS macro to generate choice designs. That's the kind of design you get with no level overlap at all, no constant attributes at all. And you can also ask for partial profile designs when you use our algorithm and the utility neutral approach. These are the designs, but I will skip them and move to the table with our efficiencies. Here on this slide I will summarize all the efficiencies of the designs that I've shown. As I said, the full profile design created using the Bayesian d-optimality criterion is the one we use as a benchmark. That's the design we use in the ideal scenario where the respondents have unlimited cognitive capabilities and can handle any number of attributes. In that case, our dB value is 11 and a bit, 100%. Now, if we have one constant attribute in every choice set, then the informational content as measured by the D criterion value drops. And you can see that it drops more if we use the attribute balance approach than if we use the variance balance approach. It seems that if you have to decide on what attributes to hold constant, the variance balance approach here does substantially better than the attribute balance approach. We observe the same phenomenon when we generate designs where we hold two attributes constant. Here too, the variance balance approach, and we have two slightly different versions of that, does better than the attribute balance approach. And you can see that the informational content of our experiment drops even further when measured by the d-optimality criterion, the Bayesian d-optimality criterion. That's the statistical information content. Of course, the loss in statistical efficiency here is compensated by the fact that the respondents probably give more reliable answers because the choice task is more doable, and because probably they will not switch to lexicographic choice behavior because they get tired of evaluating the choice sets. So that's for the Bayesian d-optimal design approach. What about the utility neutral approach? Well, the Bayesian d-optimality criterion for the full profile utility neutral design is only 8.77. So you can see that this design performs substantially worse than all but one of the designs we have here. So even though this is a design that assumes unlimited cognitive capabilities of the respondent. And if you have constant attributes in the utility neutral design approach, the informational content drops even further. And that brings me to the last slide. I've shown you a method that can help you to design choice experiments when you have many attributes and you want to save the respondents a little bit in your study. it turns out that the variance balance approach we have to decide on the constant attributes is substantially better than the attribute balance approach. So we would recommend that variance balance approach for future work. And the outperformance of that variance balance approach is constant over all possible scenarios that you can think. Now, I mentioned a couple of times that we have two slightly different versions of the variance balance approach, and it turns out that one of them is better than the other, and the difference between the two increases with the number of attributes and the heterogeneity between the numbers of levels of the different attributes. I didn't go much into that, but that's going to be in detail in our paper. And then one final remark that I have is that there are also some theoretical results in this area, and these theoretical results will be discussed in the next talk by Heiko Grossmann. And in some specific situations, the designs that he derived outperform the ones of our algorithms, and we're still trying to find slightly better ways of doing things. So we're still trying to improve our algorithms so that they match those of Heiko in those specific situations where he does better presently. That's the end of it. Thank you for your attention.
Yeah, John. Can I ask the audience, how many of you are familiar with the literature in consumer behavior and in psychology on missing information? Can I see a show of hands? One, that's what I figured. There's a 25-year literature on what happens if you omit attributes. The answer is that the subjects infer them. And when the subjects infer them, that produces a correlation with the random component and gives you all sorts of problems. So while I love the work mathematically, you're now taking us back to a situation where we know that in fact the humans are doing this. The literature is absolutely, confirming this in study after study after study. I've had at least 3 PhD students myself work in this particular area. So you have to be, this is the thing I try to tell you guys in design. Humans are not inanimate objects, and they interact with designs. So you've really got to care about not just the statistical and mathematical properties of designs. You also, unfortunately, have to care about the demand characteristics that are associated with what happens when you implement the designs. So I really, if I could give this group one piece of advice, is you've really got to work with psychologists when you design these things so that you don't make fundamental mistakes about creating things that are outcomes of the designs that shouldn't be there.
But strictly, they're not missing, are they? They're just held constant.
Yeah.
So
Same deal if they're held constant.
Well, here in this choice set, for example, the respondents don't have to infer levels for the 7 attributes, for the 4 attributes that are held constant, simply because a choice has been made for the level of these attributes. So here, the respondents don't have to infer.
Yeah, but then your
anything.
argument about you reducing the amount of information, the only reduction you have is in that they don't have to consider the differences. But I mean, the information's still there. So the subjects actually have to read the information and they have to decide and see for themselves that in fact it's constant so they can ignore it.
But they have to evaluate fewer differences, and that helps a lot.
Well, maybe, maybe not. I just really think you need to think about this psychologically rather than statistically.
Comment on that. You said earlier on that people can make a choice from a wide range in a shopping shelf. But maybe the choice they make could be one of many, and the choice therefore is not all that difficult. They don't think about it a great deal, but when the choices are much more complex, it could be much more difficult.
The comment I made earlier was really that we don't know. So my appeal really is, can we agree on, a systematic program of research here so we can get some answers rather than just speculating on it and forming opinions about it. That's all.
I was wondering, Peter, is it possible to come up with some general conjecture about whether the unrestricted or the restricted designs are going to be better, for instance, in the utility neutral case?
Statistically speaking, the unrestricted designs are going to be better because they score better on the de-optimality criterion. But I think it's really unelegant if you have choice sets that sometimes vary in 3 attributes and at other times they vary in 4 attributes. And I think this creates confusion, and I would always avoid that.
But in the utility neutral design case, I don't think this is an issue because you're using the linear optimality criterion, and then you will always get minimum level overlap. So the unrestricted case is similar to the restricted case there.
Yeah, and I agree. So in the case where you assume that the betas are 0, there it doesn't matter whether you use restricted or unrestricted. The result's going to be the same.
Okay, thanks, Peter. Again, we need to move on because